Okay, the next one is admission to a ball game. It just seems like dollars and cents are always easier things to figure out because, well, it's money. So here, let's define our variables. We have general admission and we have reserved tickets. So let G be the number of general admission tickets. And we're going to let R be the number of reserved. Okay, I see that there was a total of 1298, so G plus R is 1298. And then the next equation is $5 for general admission, so 5G, plus 6.5R is equal to the total amount of receipts, which is 6,946. Okay, I just think it's going to be easier to plug in for G. Or do you want to multiply it by -5? What do you want to do? You want to do elimination this time? Okay. So you multiply by -5. Rewrite this. So -5G minus 5R equals, and then I do -5 times 1298. Okay. So what we can do is, here, just to be consistent, I'm writing the second equation underneath. Now I want to combine them. I have 1.5R equals, so this minus this ends up being 456. If I divide 456 by 1.5, I get R is 304. So I have 304 tickets that is reserved. So that's why it's important for you to remember how you defined your variables. And remember, the total number of tickets was 1298. So I can just do 1298 minus 304. And that's the total general admission. Okay, that concludes 9.1 with our applications. 9.2 we started yesterday. And then we ended with 22. So I'm introducing Gaussian elimination. And what this method is we are going to set up a matrix, an augmented matrix. And with Gaussian elimination, we are trying to get to an upper triangular matrix. So upper triangular matrix. And what it looks like is I have ones down the diagonal. These are ones. I have zeros underneath. And then I have a bunch of numbers here. They could be zeros. And numbers here. So that's Gaussian elimination. So I write my matrix. So remember, you have X in the first column, Y in the second column, and your constants that augment it. So I have 1, 3, 2, 5, 7, and 18. So there's my augmented matrix. I want it to look like this. So the first thing I do is they call these pivot points are your ones. I already have a 1 here, so we're good. Now I just need to make this 5 a 0. So remember how we eliminated variables before? I want to eliminate the x in the second equation. And so we're going to do row operations on this. Remember, I want to multiply row 1 by -5, and then I'm going to add it to row 2 to make my new row 2. Okay, so this is the notation that I use. So when I do this, my first row does not change. It's still 1, 3, and 2. My second row, I know this is going to be a 0, right? Because -5 times 1 plus 5 is 0. That's the easy part. We did that part on purpose. What is our consequence for doing that? We'll have to multiply -5 times 3, which is what? -15. -15 plus 7 is a -8. Yes. Okay. So another consequence of this is I need to multiply -5 times 2, which gives us -10, and add that to 18. Well, 18 minus 10 is 8. Okay. Here's my new matrix. It's not quite an upper triangular matrix because what I need now is I need another 1 in the diagonal. My next pivot point is going to be this -8. So how do I make -8 1? Yes, I'm going, well, yeah, divide by 8 and divide by -8. So I'm going to do row 2 divided by -8, basically. It's my next mission. So the first row doesn't change again, so I have 1, 3, and 2. My bottom row, it doesn't matter. If I take 0 and divide by -8, it's still going to be 0. Okay? That's the beauty of making it 0. I don't change anything. -8 divided by -8 is 1. And what is 8 divided by -8? -1. Okay. So now we are at our Gauss elimination. And now we're going to start back solving. So remember, this is x and this is y. What this last line tells us is that y is equal to -1. Okay, and then I have to back solve. I use the next equation, x plus 3 times y, which is -1, is equal to 2. Do you see what I did? I just substituted. So it's basically x minus 3 is 2. So I have to add 3 to both sides. X is 5. So I have one solution. X is 5 and y is -1. Okay, so that is Gaussian elimination.